Chapter 24, Electric Potential. Now, electric potential is different from electric potential energy, and that should be clear in our mind that potential energy and potential are two different things. So electric potential is not the same as electric potential energy. And we'll see what is electric potential energy, and we'll see what is electric potential. So let's consider two parallel plates. The lower plate is negative and the upper plate is positive. So there will be a uniform electric field going from the upper plate towards the lower plate. We will just show a few lines. There will be more lines in here. Now at this location, if we have a positive charge it's held over here, that's the point A, and if we release it, there will be a force on this charge which we can write as Fe, and that electrical force on it is going to be Q times the electric field. Q is the charge and E is the strength of the electric field. That will be the force, and it's going to be a vector. The force is in the same direction as the electric field because this is a positive charge. Now we had seen earlier that the work done is F dot ds, a force dot the displacement of an object. So if we want to find the work done when the particle moves under the action of this electric field from A to a point B, then that work we can write the force as a QE dot ds. So that will be the work done when the charge goes from A to B. Now this work will be done by the electric field on this charge, and what we would now like to do is to find the difference in potential energies, or the loss or gain of potential energies that this object has when it moves from A to B. So we write a delta UE as the electric potential energy, and that will be equal to the negative of the work, so it's going to be minus QE dot ds. Now why is it negative? So let's consider Q to be positive. The electric field is downwards, so the electric field is going to be a negative J, and we dot it with ds, and ds is going to be negative J and times the Q, so J dot J is 1, and a minus will give it a plus, so this whole thing is going to be QE and a ds. That will be the magnitude of this. Now the potential energy is going to be decreasing as it goes down because it's going in the direction of the field. Similar to if we have a gravitational field, if here's the surface of the earth and you have an object that's falling downwards, going towards the direction of which the force is pulling it, then there's a loss of potential energy, which is given by mg, which is the force, times the delta y, and the delta y is a negative number, so it will lose potential energy. Similarly, as this goes downwards, it's not downwards but towards the negative plate, it will lose potential energy. That may convert into kinetic energy, but the potential energy will get smaller. Or we can look at it another way. If you have the positive charge here and we push it upwards, as we push it up, we are applying a force that's upwards and a displacement also upwards, so we will be doing work on this object, and so the potential energy will increase, and that is like lifting an object from here to a certain height above the earth. So as you lift something up, you increase the potential energy, and the same thing would happen if you go this way. So the delta U is written as a minus QE dot ds, and if we go from points A to B, we can write that as a delta UE from A to B would be the integral from A to B of QE dot ds. And this would be a general equation. The electric field here was uniform, but here it may not be uniform, and ds does not have to be in that direction. It could be in any direction. So we do this integration, and that gives us the change in potential energy as we go from point A to point B for a charge Q. Now the electric potential is written as a V. That's a symbol for the potential, and this is defined as the electric potential energy divided by the charge. So it's the potential energy per unit charge, because that's the potential energy per unit charge. It's like the gravitational potential energy per unit mass. That would be like a gravitational potential. So electric potential is the energy per unit charge. And we can write the V as a UE, which is the electric potential energy over Q. And so the difference in potential between 2 points, also called the potential difference, which is a delta V between the 2 points A, B, would be given by 1 over the difference in potential energy. That's going to be delta U A to B over Q. If you divide that by Q, this becomes, the Q's will cancel, and it will be simply minus E dot ds. So this is the equation for that's from A to B. That's the equation for the change in potential energy. Now the units of energy are always joules. So that's a joule. And therefore the unit for potential will be joule over coulomb. So potential is a joule per coulomb, and similarly the potential difference is a joule per coulomb. And this is called a volt. So 1 volt is 1 joule per coulomb. The symbol for volt is also a V. So potential is written as a V, and the unit of potential is also a V, which is a volt. And that sometimes gets confusing, but you should remember as you look at the context whether it's the unit or it's the potential. Now we can also write it slightly differently. If we take this equation and we say that this is from here, the delta V is an E dot ds. So this is a volt. The electric field is newtons per coulomb, and the ds is a meter. So the Newton meter would become the joule per coulomb, but we can also write this as volts per meter is newtons per coulomb. So that's the electric field, and that's a electric potential over a distance. So the electric field is in a way the rate of change of potential with distance. We now find the electric potential at a distance r from a point source, from a point charge. So what is the electric potential at a distance r from a point charge which is Q? So let's say that here is our point charge, which is Q, and it's a positive charge, and here is, let's say, the electric field going outwards in all directions. So that's the electric field, and we start off from point A and we go to another point B somewhere here. So there's an electric field line also passing through here, and we take a path that's like this. So we go from A to B along this path. And so the difference in potential between these 2 points, delta V AB, is, as we had before, it's going to be minus integral of E dot ds. So the electric field is pointing this way, and the ds is going upwards, and then it's turning. Now the electric field at any point due to a point charge is given by kq over r square in the direction pointing away from the positive charge. That's going to be minus integral of kq over r square, r unit vector, and dot ds. And we do the integration from a to b. Now let's look at this r dot ds. So if this is our r unit vector, so it's of length 1, so it's going to be pointing this way. This is dr, this is r unit vector, and the length is 1 unit by definition, and the ds is going this way, so the ds is like this. It does not have to be of length 1. That's our ds. Then r dot ds is going to be the magnitude of r times the magnitude of ds and the cosine of the angle between them. Now the magnitude of r unit vector is 1, and the magnitude of the ds vector is ds, so we write this as ds cos theta. So r dot ds is simply ds cos theta, and this is a scalar, and we can replace the r dot ds with r ds, and so our delta v AB becomes minus, we can take the k outside and the q outside, so it becomes kq, and integral r dot ds becomes ds cos theta over r square. Now we need to resolve ds cos theta. So if this is r and that's ds, we drop a perpendicular over here, so this angle is 90 degrees, then this distance is ds cos theta. And we can write this ds cos theta as a dr, where the dr is a vector in the direction of the unit vector r, or in the direction of the electric field, but this is not a unit vector. So this becomes minus kq, and ds cos theta becomes dr over r square. Now the integral of this ds over dr over r square is simply minus 1 over r, and we have the limits from a to b, and that becomes minus kq. We can take out the negative, and with this negative make it a positive, and apply the first limit. Upper limit becomes rb minus 1 over ra. So it becomes kq times ra, which is this distance, and rb, which is this distance. So this is ra, and this is rb, just their magnitudes. If we take ra as very far away, then 1 over ra times this would become 0. But we define that at a great distance, when any distance tends to infinity, then we'll say that the potential at a very great distance tends to 0. So that's something that we say, that the potential at an infinite distance is 0. Well, this could also have been written as kq 1 over rb minus over rb minus kq over ra, or v at b minus v at a. So that would be the delta v from a to b, vba minus va. And va over here is taken as 0, and therefore the potential at b is simply kq over rb. And so that is our general equation, that the potential due to a point source, a point charge, is kq over r square. Now we do an example. Let's suppose that we have a charge, positive charge, Q, and Q is 3 microcoulomb. We want to find the potential at a point P, and the distance from here to here is 10 centimeters. So R, magnitude of R is 10 centimeters, and well, it has some direction. Then the potential at P is going to be kq over R. That's going to be 8.99 into 10 to the power 9, and the units would be Newton meter square per coulomb square, and the charge is 3 microcoulombs, so it's 3 into 10 to the power minus 6 coulombs divided by R, which is 10 centimeters, so it's 0.1 meter. Now we can see that one of the coulombs will cancel and one of the meters will cancel, so we'll be left with Newton meter per coulomb, which is a joule per coulomb, which is a volt, so the units are okay. And now when we multiply these together, we will get 27 0.010 to the power 4 volts. So that is the potential at this point. It's 270 kilovolts. That's a V. Now if we want to find the electric field at this distance, just the magnitude of the electric field, that is going to be kq over r square, and substituting these values, it's just going to be divided by another 0.1, so it's going to be 10 times bigger, 27 into 10 to the power 5 newtons per coulomb, and it will be in some direction. That will be the direction of the electric field. So if we know the angle, we can write the angle over here.